Alright, suppose we had two thermal reservoirs. So this one up here and this one down here. There are two different temperatures. This one's hot, this one's colder. And we want to put a heat engine in there. So this could be anything from, there's these little Peltier type devices, or okay, so one good example, take the New Horizons probe that just went to Pluto. It's powered by a radioactive heat source, which is then, it has heat sinks around the outside, and there's a temperature gradient between the radioactive, the plutonium oxide, or whatever they're using, core of this device, this battery, right? And then the heat sinks on the outside that radiate the heat into space, and then they can put sort of thermoelectric devices in between, and they're able to pull electricity off of this. So this is just one example of a heat engine. You could also think of like a steam locomotive or something like that. So the question we want to ask is, suppose we have two, in this case, we're not dealing with radioactivity or anything, or adding wood to the fire. Suppose we just had, say, a block of copper and a block of steel, something like that. And one's hot, one's cold, and we want to put some sort of heat engine in between, whether we're boiling water or just converting it directly into electricity. But we want to know the maximum amount of work that we can get out of this system. And we're going to treat these sort of in a general way, so that each these reservoirs are actually finite. Okay, so basically they will both eventually reach the same temperature, come to equilibrium, and then we'll not be able to get any more work out. So first, what we're going to do is we'll just do simple addition, like conservation of energy, right? That there's one arrow going in and two arrows coming out, so this one going in must equal these two. So the energy going in, EH, is equal to W plus EC. All right, so we can solve this for our work, which is W is equal to EH minus EC. Okay, so now what are these different energies? Well, they each have a constant heat capacity. All right, so the temperature difference multiplied by this heat capacity is how much energy they've either gained or lost. All right, so we'll do this in two lines. All right, so right, so okay, so we need to find EH first. All right, EH, the heat capacity of this one is CH. All right, and then the temperature difference, it's going to go from a TH to the TF. All right, and TH is larger. We're just working in absolute magnitudes, so we want these numbers to be positive. So TH minus TF. We don't know what TF is yet. That's the main part of this problem that we'll have to solve. All right, so that's this EH part, and now we'll have a minus sign. All right, this is still part of this same equation on two lines again. Okay, so now we're looking at this E sub C right here, and so we want to know how much energy is gained by this one. So this time we expect this one to warm up, so the final temperature TF is going to be larger than T sub C. All right, so great. Let's just rearrange this really quick. We're just going to have CH, TH plus CF TC, okay, and then minus CHTF minus CCTF. Alright, so we could combine these terms if we want to, but so we've solved the problem, except we don't know what the final temperature is, right? So suppose we weren't taking any energy out in the form of work, right? These would just come to the same temperature, which is it would just be just based on the heat capacity, sort of a weighted average of their temperature. So just in the case of, say these two were identical, right? The same material and the same amount of material, they would come to just the average of TC and TH. So TH plus TC divided by 2. But that's not necessarily the case here. Plus, we're taking the work out, right? So we expect that you know so let's see what's going to happen. There's not quite as much energy to go around, so what we would expect them both. So we expect the final temperature to be slightly lower than it would have been without this. Okay, so the question is, how much can we get out? All right, so for this we need to know what conditions are required for the total entropy of this system, or the universe, right, to be to increase or stay the same. So if it's a quasi-static infinitesimal type process, then the change in entropy should be 0, but it's not going to be less than 0. It'll be either greater to or equal to 0, greater than or equal to 0. All right, so so let's go ahead and look at the change in entropy. Okay, so basically what we're going to be doing is using this equation. I'm just going to label this one H, I don't know. I'll just put a little H right here. Okay, so this is our change in entropy up here for this hot one. Okay, and we'll do a similar one for C. Okay, and this is going to be, well, greater than or equal to 0. Okay, so first of all, dq. So that's his units of energy. So we know we just have to if we have an infinitesimal change in the temperature, we just have to multiply it by C, whatever that is. All right. So let's go ahead and do this. All right. So the first one we are this time we'll just go from initial temperature to final temperature. All right. So TH to TF, right? And the heat capacity, so this C for the first one is just CH. CH, and we'll have a dt divided by this T. All right, now we'll do our second one. We start at TC and go to TF. All right, and this time our heat capacity is C sub C. And we'll divide by T. Okay, so we can get a little space here. Just bring this out like this, and we have a natural log of T, and this is going to be evaluated from TH to TF. And for this one, natural log of T. This one's evaluated from TC to TF. All right. Okay, I think we're good so far. So let's go ahead and plug these in. So we're still looking at the change in entropy. All right, and again, this is going to be greater than or equal to 0. Okay. So we have a CH, and we have natural log of TF minus natural log of TH. Okay, and I'll come down on the second line here, plus C sub C, natural log of TF minus natural log of TC. All right, so the one that's increasing in temperature, right, is going to be increasing in entropy, and the one that's decreasing in temperature should be decreasing in entropy. But this all, of course, depends. Like how much depends on these C's and the T's and things. Okay. Let's just, what should we do now? Let's try and bring the terms with T sub F together. Okay, so I'm going to do a CH plus CC, like this, and we're bringing these, those are both multiplied by natural log of TF. Okay, now we have a minus CH ln of TH, and we have a minus CC ln of TC. All right, and remember this is greater than or equal to 0. So for the maximum workout, we want to have this be equal to 0, right? Because we get the maximum amount of workout when we're doing an infinitesimal quasi-static process, and the entropy change is 0. So I'm just going to go ahead and set this equal to 0, just so we find the maximum. All right, and then I'm going to bring these two terms onto the other side. So we just have a CH plus a CC. Natural log of TF is equal to CH ln of TH plus CC ln of TC. All right, so we just have to solve this for TF. So what we're going to do is just, we have all of our temperatures are positive. I don't think we have to worry about anything crazy going on with our natural logs. Yeah, I'll write this out real quick. Okay, so what do we have when we something like this, and then we have TH to the CH and a C to the CC. Okay. And units are always kind of weird when it comes to when you start throwing natural logs in and stuff like that. That's an H right here. Okay. Yeah, so basically we have I didn't do this right, did I? This should be, oopsies, excuse me, a 1 over CH plus CC. Okay, so yeah, weirdness, right? Even though these carry units, and the temperature has units on it and whatever, they kind of divide out at the end. So yeah, kind of weird. All right. Okay. And let's just write this in maybe more This way we'll see that the units work out. So this is to the power of CH divided by CH plus CC. Okay, and then we're multiplying by T to the CC over CH plus CC. All right, so these are dimensionless up here, so it does work out. All right. Oh, this is a TC. Okay. All right, so now all we have to do is take this T sub f and plug it back into our original answer way up here. So the maximum amount of work we can get from a system like this is the following. I'm going to go ahead and combine this CH and CC this time. All right, well, I'm not going to write this out. Right, so here we go. Here's the TF, and that's equal to this. All right, so you can just substitute that in by yourself. It would get too confusing if I wrote it all. So this is probably more clear. Right, so yeah, the maximum amount of work that we can get from the system of two finite reservoirs. And okay, so real quick, let's just look at the case. Suppose that these two reservoirs were exactly equal. All right, the same heat capacity, meaning they're made out of the same material and they have the same size or mass or whatever. They can hold the same amount of thermal energy. Then let's just do a special case. So I'll just write the word case here. Say that CC is equal to CH, right? So they hold the same amount of energy. Now let's just look at what the work is, just so we can get this. So work. All right, I'm just going to call this C. All right. So I'm gonna bring C out of this whole equation. All right. So here we have a TH plus TC minus, we have two of them here, so minus 2 TF, and we'll go ahead and write that out this time. So we have a TH, all right, and if these are equal, then this just becomes a 1/2, okay, and a TC to the 1/2. All right, so that is equal to C. TH plus TC minus 2, and then we'll just put this all under square root TH TC. And there we go. So if the two thermal reservoirs are equal in heat capacity, then this is the answer that we would get. All right, and just real quick, suppose that we started out with two temperatures that were the same. We should be able to get nothing out of it, right? So in the case where the heat capacities are the same and the temperatures are the same, I guess the heat capacities shouldn't even have to be the same in this case, right? What we get here, work is equal to C times, all right, so here we have 2T, so if these are just equal to T. So 2T minus 2, okay, so the square root of T squared is just T. So we do get 0 here at the end. Let's just check that real quick for the general case. Here it is. All right. And you can see that right away. If these are all T, so for TC equals TH equals T. This work is going to be just CHTH plus CCTC minus CHT. Oh, I forgot to. Getting sloppy here. CHT minus CCT. Alright, so this and this will cancel, this and this will cancel, and again, we will not get any work from any system where the two reservoirs are at the same temperature, which is obvious, but good to just as a way to check our answer to see if it's reasonable.